Welcome back. So this is the third video in our review of Unit 4. So we're going to go ahead and go through questions 14 through 19, and hopefully by the end of this you will be prepared beyond belief for your unit test or prepared for the AP exam, whichever one you're getting ready for right now. So for number 14, it's giving us a table of the second derivative values of f. So let's see here. When x equals 0, we have a second derivative of 5. When x equals 1, we have a second derivative of 0. When x equals 2, we have a second derivative of negative 7. And when x equals 3, we have a second derivative of 4. So in this case, it's giving us the second derivative, and it's asking which of the following statements are true. And so I want to kind of go through each one of these options here and explain why they must be true or why they must not be true. So for option A, it says f is increasing over the interval 0 to 2. So we're going to refer to our chart here. F is increasing when f prime is positive. Notice the chart has nothing to do with f double prime in this case. F is increasing when f prime is positive. Because I was given f double prime, I can't conclude anything about f being increasing in that case. So option A doesn't make any sense. Option A is false, or at least we don't know if it's true. It doesn't have to be true. And that's because f double prime says nothing. Let's see, tells us nothing about f increasing or decreasing. Now, I'm not asking you to justify that on any test or anything like that, but that's just a good reason to understand that. So A is false. And then for option B, it says f is decreasing. For the same reason, there's nothing about f double prime that tells us whether a function is increasing or decreasing. So now we could say that since f double prime is positive at 0, that f prime would be increasing over some interval with 0 in it. But that's a false statement as it stands. Option C, it says that f has a local maximum at x equals 1. Well, if we look at x equals 1 here, we notice that f double prime is 0. This is deceptive for some students, but not for mine because we know the chart. Hopefully, right? If f double prime is 0 here, and we see that f double prime is positive on this side and negative on this side, we kind of view that and say, oh, well, look, we are changing signs at f double prime, so therefore there's something happening here. And that's generally true. The problem with that is that this is a table of values. This table of values doesn't tell me what's actually happening for values in between 0 and 1 and in between 1 and 2. So we could actually go, like f double prime of 0.5 could be negative 2, which implies that we went from positive to negative over that interval, right? So we don't know what's happening in the in-between of each of these intervals. So we can't conclude whether there's anything actually happening at f double prime or at x equals 1 here. It appears that there might be, but we don't know if it actually is taking place. So if we think about this, we know that we have a local maximum when f changes from increasing to decreasing. Or we can interpret that as saying when f prime changes from positive to negative. But there's no interpretation with f double prime for the same reason that A and B were false here. We can't look for a change in direction by looking at f double prime at all. But then you might say, well, if that's the case, if C is false, then let's go down to option D, because option D sounds really good. Option D says the graph of f has a point of inflection at x equals 1. Well, for a point of inflection to occur, that is when f changes concavity, right? Which means that f double prime changes signs. Well, so if a point of inflection is when f double prime changes signs, we see that we are positive, f double prime is positive at x equals 0 and negative at x equals 2. So, and then we also see that f double prime is 0 at x equals 1, so it's easy for us to conclude that there is a point of inflection at x equals 1. But remember, a point of inflection requires that f double prime changes signs. Maybe it didn't change signs at x equals 1. Maybe it was positive, went to 0, went back to positive, and then went back to negative somewhere between 1 and 2. Or maybe it was positive at 0, and then went to negative somewhere in between 0 and 1, and then went back up to 0, and then back down to negative again. So we don't know where f double prime changed signs. The only thing that we know is that f double prime did change signs. So we can't say definitively that it did change signs at x equals 1. It appears that it does, but we can't guarantee that. So we would say that D is false because we don't know if f double prime actually changed signs. We'll ask this question, does f double prime actually change signs when x equals 1? And we don't know that, so we can't conclude that there's a point of inflection there. But we can conclude for option option E, used to my grading scale A, B, C, D, F. For option E, the graph of f changes concavity in the interval 0 to 2. So we do change concavity because our f double prime was positive and it went to negative. So that means it must have changed concavity somewhere in that interval. And so that makes E the only must be true statement in this list. Okay, for number 15, this is going to be a calculator problem. Because you can see that f prime is actually a really gross function, cosine of e to the radical x. So let me pull that up on my calculator here, number 15. All right, so it says that f prime of x is equal to cosine of e to the radical x. And it says, how many relative extrema does f have on the interval 3 to 7? So I'm just going to write down for 3 is less than x is less than 7. So we're looking for relative extrema. The way we look for relative extrema is by first finding our critical points. And going back a little bit, the critical points are when f prime equals 0, f prime does not exist, or at endpoints. I want to point out that our interval does not include the endpoints, so the endpoints are not critical points because there are no endpoints here. We're not looking for absolute extrema, we're only looking for relative, so we don't even have to consider these endpoints that aren't really there. So the first thing we have to look for is when f prime is equal to 0 and when f prime does not exist. So actually, before I do that, I want to go ahead and justify what I'm looking for here. It says, how many relative extrema does f have? Well, my justification for what I'm looking for is f has a relative extrema when f prime of x changes signs. Okay, so that's my justification that I'm going to work off of here. So since I was given f prime, I've related my justification to f prime, and now we're simply looking for a change in signs. Well, it gave me f prime, so I don't have to take the derivative. I just need to figure out where it changes signs. So we've got to find our critical points. Our first critical points are when f prime equals 0. So we're going to set that function equal to 0. And I do not expect you to be able to solve that equation in and of yourself. I want to look at the graph, so I'm going to go ahead and type that into my y list and look at the graph and then find the zeros. So what we'll notice is that in the interval of 3 to 7, we have an x-intercept of 4.248. We have another one at 5.748. And we actually have another one at 7.016, but that one's past our interval, so we don't have to consider it. So now I'm going to look at my number line, just because I like it. Number lines help us understand things in very simple ways. So that is my number line for x's. And then f of x, we're going to note by looking at our graph here that we had a 0 at these 2 points, and then these guys were our endpoints, kind of, but it's open interval. So if we look at our graph from 3 to 4.28, we see that the derivative is above the x-axis, so the derivative is positive. Sorry, this is f prime. And then the interval from 4.2 to 5.7 is going to be negative, the derivative is negative, and the interval from 5.7 to 7, the derivative is going to be positive here. And again, don't just assume it bounces back and forth all the time, because sometimes you do get positive, positive, negative, and so on. But there we go. How many relative extrema do I have? Well, relative extrema occur when f prime changes signs. We see that we have a sign change at 4.248 and 5.748. And so we can conclude as an answer that we have 2 relative extrema, okay, for that open interval. Just a side note, if that was a closed interval for both of those, then that would imply that there is a relative extrema at x equals 3 and a relative extrema at x equals 7, because they're endpoints, and whatever's happening just to the left of this endpoint, this is either going to be higher or lower than the point right next to it. And then same thing on this side. Okay, so, but since it's an open interval, we only have 2 relative extrema. All right, for number 16, this is a little bit of a tricky problem because it's gross, first of all. We're given f prime of x. And let's see, f prime of x is the cube root of 2x minus 4 over natural log of x. And it's asking for us to find the x coordinates for the inflection points of the graph of f. Well, this is going to be a calculator problem. I think we can conclude that pretty easily. We're looking for the points of inflection of f. Well, points of inflection for f occur when f changes concavity, which implies that f double prime changes signs, or f prime changes direction. Since we're working through this analytically, we can't justify where f prime is changing direction by just looking at the function itself. So we have to look for a change in signs, and that's usually where we have to justify anything anyways, unless we're given a graph of something specific. So we're looking for when something changes signs. F has a point of inflection when f double prime changes signs. So I'm going to write that down. F has a point of inflection when f double prime changes signs. So right there, that's earning us a point, because that's telling the reader that we know what we're looking for. Now from here, we're going to have to take the second derivative. Since we're given f prime, we only have to take the one derivative of this, but it is a gross one. So to find the second derivative, given the first derivative, here we have to apply the quotient rule. Now, before we do that, I'm going to go ahead and rewrite this radical expression as a rational exponent. So instead of the cube root, I'm going to rewrite it as raised to the 1/3. That will help me to take the derivative a little bit easier. So quotient rule says the derivative of the top. So to take the derivative of the top, I have to use a chain rule. So it's going to be 1/3 times 2x minus 4 raised to the negative 2/3, because I have to subtract 1 for the power rule, and then times the derivative of the inside, so times 2, and then times the bottom, so times natural log of x, and then minus the derivative of the bottom, which is 1 over x, times the top, so then times 2x minus 4 to the 1/3, all over the bottom squared, so that's the natural log of x squared. Now I want to be careful on the bottom here. If you just put natural log of x squared like this, what you're saying is that you're squaring the x. We're not squaring the x, we're squaring the natural log of x. If I write it like this, then somebody might misunderstand that I can use the power rule here for logs and move this 2 up front. I cannot do that because I'm squaring the whole function there. So there's my second derivative. Now I have to look for where the second derivative changes signs. Well, I'm gonna clean this up a little bit so I have something a little bit easier maybe to type into my calculator. I'm gonna move this 2 out front here, so I got 2/3 times 2x minus, times 2x minus 4 raised to the negative 2/3 times natural log of x minus 1 over x times the cube root of 2x minus 4 all over natural log of x squared. So there's my second derivative. Now the next step is to figure out where this guy changes signs. So I'm going to go ahead and set this equal to 0. And I know there's a lot of writing going on here. So 2/3 times 2x minus 4 raised to the negative 2/3 times natural log of x minus 1 over x times the cube root of 2x minus 4 all over the natural log of x squared. So we're going to graph this in our calculator, graph the second derivative in our calculator. The problem with this particular problem is that everything is happening really close to the x-axis. And so when you graph it on a standard window from like negative 10 to 10 and negative 10 to 10, you're not going to be able to see what's going on there. So you need to probably change your window so that you can see really close to the x-axis. So what I like doing is, because we're looking for a change in the signs, I like changing my y-axis, my window for the y values, to be something like negative 0.05 to positive 0.05. And then for the x's, I'll notice that this function has a natural log in it, which means that the domain of this function is all positive numbers, because you can't take the natural log of a negative number. So then my x minimum is going to be 0, and then my x maximum, maybe I'll put that at 100 and see kind of what's trending here. And I can kind of get a better idea of what this graph looks like. So if you change your window to be from 0 to 100 and from negative 0.05 to 0.05, you can see a lot more about what's going on in this graph here. So I'm going to give you kind of a quick sketch of what that looks like. The second derivative on the graph with this really weird scale looks something like this as a graph. And so we can see that the second derivative hits the x-axis at those 2 points. And those 2 points are in fact x equals, let me get rid of this here, x equals 3.35 and 12.362. Okay, so those are those 2 values. And now I can set up a number line here starting at 0. And we could say 3.35 and 12.362. And that keeps going here. So this is my x-axis. And if I look at my second derivative is going to be 0 at these 2 points. This is going to be an endpoint that's not included because you can't take the natural log of 0, and it's going to go on forever. We can see the signs of our second derivative graph here. We can see that it's positive in this interval because it's above, negative in this interval, and then positive in this interval. And now we're looking for points of inflection. Points of inflection occur when f double prime changes signs. And as a result, we can conclude that points of inflection occur when x equals 3.35 and 12.362. And that's our answer for number 16. So for number 17, we're given the graph of f prime, and we're looking for which statements are true here. So what I want to do, I want to actually graph this function here so I can point at it, really. We have kind of, it's a little tough to graph, I guess. Oh boy, we got a lot going on. So we got a high point there. We have a 0 at 3, negative 3. We have a 0 at 2. And then we have points. Let's see. How do we want to do this? It goes up, kind of flattens out. And it goes up again, and then peaks out, and then down. And then, let's see, kind of passes through there. And it kind of does something like that. Okay, so that's the graph of f prime. And we are looking for which of the following statements is true. So option 1 says that f has a relative minimum at negative 3. Well, here's negative 3. Here's negative 3. Let's see. F has, let me write down the justification, has a relative minimum when? Well, f has a relative minimum when f changes from decreasing to increasing, or we can interpret that, we want to change that interpretation to be f prime. So f has a relative minimum when f prime is changing from negative to positive. So when f prime changes signs from negative to positive. So if we can see this in the graph, then we have a true thing. So we see f prime at negative 3 is in fact changing signs from negative to positive here. So we can conclude that option 1 is true based on that justification. Now option 2, it says that f has a point of inflection at negative 2. So option 2 says there's a point of inflection. Well, we want to take f and interpret in terms of f prime. So we would say f has a point of inflection when f double prime changes signs, which implies that f prime changes direction. Okay? Now, some students might say this is a point of inflection. It is a point of inflection on this graph. We do see this graph changing from concave down to concave up, point of inflection. But that would be a point of inflection on f prime. We're looking, the statement here for option 2 is saying that f has a point of inflection. So f has a point of inflection when f prime changes direction. So that means we're seeing the function increase and then decrease, or decrease and then increase. So we don't see that at negative 2. So we don't have a point of inflection for the graph of f at negative 2 there. And then option 3, it says that the graph of f is concave down from 0 to 4. So let me justify this. F is concave down when, okay, f is concave down, looking at the chart, right, making sure you understand the chart. F is concave down when f double prime is negative. We're not looking at f double prime, we're looking at f prime, so we have to interpret it that way. F is concave down when f prime is decreasing. So when f prime is decreasing. So where do we see f prime decreasing? Well, we see it decreasing from x equals 0 to x equals 4. And that's exactly what the statement was saying for option 3. So we could say that option 1 is true and option 3 is true. All right, for number 18, the wording on this one's a little weird, but we have to understand how to read these things in order to do well in these types of exams. It says a curve has a slope of 3x squared minus 4 at each point xy on the curve. A curve has a slope given by 3x squared minus 4 for each xy value. So what this actually means is that the slope of the curve is equal to 3x squared minus 4 given different x values. In other words, 3x squared minus 4 is the derivative. So we could write this. For number 18, we can say that y prime equals 3x squared minus 4. The slope of the curve is 3x squared minus 4. The curve slope is 3x squared minus 4. So the wording is really weird here. So y prime is 3x squared minus 4. And it wants to know the equation of this curve if it passes through the point -3, -9. So let me write this down. Point is -3, -9. So a lot of students on this, just in the past, giving this problem in the past, I see a lot of students thinking, oh, it's the tangent line. I just got to create the tangent line. No, it's not the tangent line. If it said, what is the tangent line? If it said, find the equation of the tangent line, it'd be the tangent line. It is asking for the equation of the curve, not the equation of the tangent line. So if I'm given y prime, how do I get to the curve? Well, the curve is y. So I have to take the antiderivative of this guy. So we're going to say y equals the antiderivative of this. Well, the antiderivative is doing the power rule and all our rules backwards. So far, we really only know how to undo the power rule. We'll learn about the other stuff later. So if I undo the power rule, I know that I need to add 1 to the exponent. So that's going to be x to the third. And then I have to take the coefficient, right, and divide it by the new exponent. So I'd take 3 and divide it by 3, so the coefficient would be 1 here. So then this would just be x cubed. And then the antiderivative of -4 is -4x. And then remember that all derivatives, the antiderivative of all derivatives, they're all different by a constant. So I have to put a plus c here. And so I'm going to go ahead and take the derivative of this to make sure it matches this. The derivative of x cubed is 3x squared. The derivative of -4x is -4. And the derivative of a constant is 0. So I know that I took the antiderivative correctly. Now we know that our function, our curve, passes through this point. Well, that is an x value and a y value. And in fact, to finish out the whole curve problem, we got to figure out what c is. So I've got to plug in values for x and y. So this is going to say -9 equals -3 cubed minus 4 times -3 plus c. And all we have to do is some algebra from here. So -9 equals -27 plus 12 plus c. So that's -9 equals -15 plus c. And that means c equals 6. So then we would just take c, plug it back in, and we'd say y equals x cubed minus 4x plus 6. That is our curve. Okay, for number 19, our last problem in this review, it's actually a 4-parter, and this is a good example of a free response question on an AP exam. I actually made it a little bit more in depth than an AP exam. I'll give you an example. For part A, I'm asking for where the function is increasing and where it's decreasing, whereas on the AP exam it usually just asks where is it increasing, because they assume, well, if you know where it's increasing, you're also going to know where it's decreasing. But I added those little pieces to be a little bit more thorough for your review here. So it gives us some information. Basically, the graph that it gives us is the graph of f prime, and we're looking for the answer to all these things, and all these interpretations, especially A, B, and C, are all going to be based on the chart. So let's go ahead and go through and solve these guys, or answer these questions here. Number 19, A. A says, over what intervals is f increasing and decreasing? So let me go ahead and justify this because it says to do that and we always do it anyways. F is increasing when what? Well, F is increasing when, now we look at what's given. We're given F prime, so we want to make our interpretation in respect to F prime. So F is increasing when F prime is positive. And so we're looking at the F prime graph. We see the F prime is positive when it's above the x-axis. So we can say, therefore, from -3 is less than or equal to x is less than or equal to -1. So that's the first part there. And then it also wants to know when we're decreasing. So we're going to justify that as well. F is decreasing when the opposite, when F prime is negative. And we can see in our F prime graph that we are negative when we're below the x-axis. So we can conclude from -1 is less than or equal to x, less than or equal to 3. So that is our answer for A. For B, it says find the x-coordinates of each point of inflection for the graph of F. Well, let's go ahead and justify this. F has a point of inflection when points of inflection occur on F when F changes concavity, which means F double prime has to change sign. So I'm going to write that down. When F double prime changes signs, well, we're not given the graph of F double prime, we're given the graph of F prime. So we need to interpret this in respect to F prime. So therefore we would say, therefore when F prime changes direction. Now I don't like just using the word direction. If I'm using signs, changes signs, that's pretty obvious. We change signs. There's only two signs that you can have in math. You can have a positive and you can have a negative. But direction in math could mean a whole multitude of things. When we're looking at a graph and we're saying changing directions, are we talking about changing from going left to going right? Are we talking about changing from going up to going down? Or changing from going out to going in? There's lots of different directions that we can change. And so what we mean by directions is we mean from changing from increasing to decreasing or decreasing to increasing. So we want to make sure we use those words as needed in these justifications. So we see that F prime changes direction only one time in that graph. So we would say as an answer something along the line of point of inflection when x equals 1, and then I'm going to add to my justification, since F prime changes direction from decreasing to increasing. So that gives me a little bit more specifics to how it changes direction. So there is only one change in direction in this particular function, this particular F prime, but you might get more. And so if you have another point of inflection, but it's not when F prime is changing from decreasing to increasing, maybe it's from when F prime is changing from increasing to decreasing. You want to break it down piece by piece and say, okay, there's another point of inflection when x equals 2 because F prime changes direction from increasing to decreasing. So be specific on the change in direction because again, direction can mean a whole multitude of things in these questions. So I'm going to go ahead and erase part A and part B so I have room for part C. Part C is asking for the intervals for which F is concave up and concave down. So let's go ahead and justify that. F is concave up when, well, the simple answer is when F double prime is positive, but we're not looking at f double prime, we're looking at f prime. So we have to interpret it in terms of f prime. So therefore, when f prime is increasing, and then that means our answer would be from 1 to 3. So 1 is less than x is less than 3. So that's our answer for the first part of C. 19, let me put a C here. This is C. Okay, and then it also wants to know when f is concave down. So let's justify that. F is concave down when f double prime is negative, which implies f prime is decreasing. And therefore, we see it's decreasing from -3 is less than x is less than 1. So that is part C. For part D goes on a different road here. And it's actually an easy problem, but we get hung up on very simple things sometimes. It says, find the equation of the tangent line to the graph of f at the point 0, 2. So remember, in order to find a tangent line, you need two things. You need to find a point, and you need to find a slope. Okay, those are the two things we have to find for a tangent line. Well, it already gave you the point. It gave you the point 0, 2. How do we find the slope? Well, the slope of the tangent line is the derivative at the point of tangency. Well, we know the point of tangency, so we have to figure out the derivative at that point. In fact, let me go ahead and rewrite it this way. The point would be f of 0 equals 2. The slope is f prime of 0. So we have the point and we have the slope at that point. So the question is, what is f prime of 0? So we're going to look at our graph here. Now this graph's a little deceptive. I don't like the way this is written because you can come up with the right answer but do it completely wrong. F prime of 0 means the slope of the curve. But we got to be careful because we remember that this is f prime. This is not f. So if I'm looking at the graph of f prime and I want to know f prime of 0, I'm just looking for the value of the function at 0. And so I'm going to go ahead and graph this so we can get an idea of what's going on right at 0. We have something that just looks like this at that point, right? Just looking for that interval. That's -1, that's 1. So we're looking for the derivative at 0. This is f prime of x. The value of the derivative, and this is the derivative, is -1. You see that? The value of the derivative is -1. But some students might say the derivative is the slope. So I'll find the slope of that line. And you do the slope and we find out, well, the slope of this is -1. And that's why this problem is deceptive. So really the slope of this is -1. But if you think about the slope of f prime is actually f double prime. So I could conclude that f double prime of 0 is also -1 in this particular problem. It doesn't always work out that way, and unfortunately it did work out this way. So do we want the slope of the derivative or do we want the value of the derivative? We want the value of the derivative given that function. Now if this said f of x, then we would look for the slope. But we don't want this guy. We don't want the second derivative. So our tangent line is going to be y minus 2 equals -1 times x minus 0. And that is our answer for part D. So I hope that you found this review helpful. I know that it was kind of long. We had 19 questions to go over, and it was a handful of videos that you had to work through. But hopefully it shed some good light on how to approach these problems. This is great for the unit test coming up for my students. For the rest of you guys out there that might be watching this, this is great for an AP review. So go ahead and go through these questions again if you'd like. You can find these questions on my website if you want a PDF version of it. Otherwise, I'll see you next time.